All right, so let's continue here with our Kramers-Moyal path integral approach. And remember what we did up to now. We found that for non-interacting Brownian particles, we can derive an action, and this action is a function of the number density in a discrete fashion, and then we made a continuum limit such that we then can write an integral over space and time between an initial and a final time, and space over the whole domain that we defined. And then we get a structure where we do have the response field dTn minus d times the density, and then we got two terms. One term which is a Laplacian acting on I and tilde, and the other one is a nabla also acting on n tilde, but now with a square. Okay? And I explained to you that this is what you get in the continuum limit, and also that this is equivalent to a Ito-Langevin equation, where you have now a stochastic differential equation that contains the diffusion term as you would expect it for non-interacting Brownian particles, and you also get a term that characterizes the noise. And there we found, as it must be, that this is a conserved noise. So it's the nabla operator acting on a vector. So it's a divergence of a white noise term, lambda of R and T. That white noise term has unit variance. On average, it's 0. And it has all the proper delta functions. And the point is, this is now multiplicative noise with the noise amplitude appearing in the Langevin equation as the square root of the diffusion constant times the number density. Okay, so that's beautiful, because now we have, from a lattice gas model, derived the corresponding Langevin description. We can also ask, what about the continuum limit for the reaction term? So say we also have chemical reactions. And there our classical case was that K particles are transformed to L particles of the same type at a certain rate, and the rate I think I called lambda. Okay, so this could be birth, death, coagulation, all kinds of processes of that type. And there what we found is that the operator that you get is something like lambda. Okay, you have lambda times the corresponding downward counting factorial. So you have the number of particles Ni, you have the number of particles Ni minus 1, and this goes down to Ni minus K plus 1. Okay. And now you wonder, how should you turn this into a continuous form? Ni's are discrete numbers. Also k and l are discrete numbers. But you want something that's now a real field, like you have done here in the first term. You have something that's a continuous real field defined over all positive real numbers. So we need to do also a continuum limit here. And remember, before we replaced our Ni by a spatial density which is the number of type A divided by the lattice constant to the dimension d, which is the molecular volume, okay? Or the lattice size that we have. But that's really not sufficient if you think about the reactions, right? So if you think about a lattice, like a square lattice here, and then at these particular sites, which do have a lattice spacing A, you can't really expect to have a large particle number. We're talking about, small numbers here at particular lattice sizes. So that means if you want to have a continuum variable, which is really spaced out very closely, very finely in real along the real axis, you need to average over a larger domain, right? Over a domain like so, where you say you have a length scale that I call L, and on that length scale, I'm assuming there's quite a few particles that you have in this box. Okay? The constraint is that the lattice spacing is much smaller than our coarse graining scale L, and this coarse graining scale is much smaller than the system size. Okay. Else you wouldn't get a mesoscopic theory that allows you to talk about some kind of space dependence. Okay, so on that scale, we would like to do the theory. And then when you collect the factors of this parameter L, then you have L to the power dk minus 1. The L to the minus d you need in order to write the sum over all lattice sides into an integral over space. And the L to the dk you need in order to define proper rates. So L to the d to the power k. Then you have n. Now let me call those things n alpha, right? Because now I'm not talking about the number of particles at a site I. I'm talking about the number of particles for such a cell alpha. Okay? That's very similar to the idea of coarse graining in renormalization group theory, where you would exactly do this and try to infer a theory at a larger scale. But there you do it really in an iterative fashion, controlled fashion from smaller to larger scales. And then we have n alpha minus 1 up to n alpha minus k plus 1. And now I'm saying, that I'm assuming that in the limit of this L going to 0, so that I really do coarse graining, I can neglect all these terms here, the 1, the minus 2, etc., and just take the n alpha to be much larger than all of those numbers like 1 or k, such that I do get this to be an effective renormalized lambda at the scale L to the power k, and then I have here my proper density to the power k of r and t. Okay? So that's the idea. And this can go wrong, right? If reactions on the local scale are correlated in some way, then you can't do this. This assumes that there's some mixing on that scale and all kinds of correlations that could be relevant, they're not there such that I can really ignore all of this and write it like so. So you should be always critical about those kind of assumptions when you see them and not take things for granted. So that means now this coarse-grained Kramers-Moyal path integral, now with real variables, has an action, and this action has the form, which is an integral over space and time. This is just a shorthand for integrating over all space and time in a window. And then I'm writing it such that I'm taking the term dtn and I combine it with a second term where I'm doing partial integration twice. So I get here minus the nabla squared n. And that's the same kind of propagator structure that we saw in the coherent state path integral. Then we have the noise term. The noise term is dn nabla I n tilde squared. So that's diffusion. That is diffusion noise. And the term that we now derived is a minus lambda n to the k I n tilde k minus L minus 1. And that is the reactions. And really all of the features that you see in the reactions. This is not just the deterministic term that you find in the reactions. If you spell this out and you would Taylor expand what you have here on the right-hand side, you would find this contains the reaction terms as you would find it in a mean field theory, but you also do get from that the corresponding demographic noise that defines the fluctuations in the chemical reactions, which is analogous to the case of diffusion noise, just a different origin of the noise. So deterministic and demographic noise, both of it you will get here. And for you as a tutorial, because we have done this, try to compare with the coherent state path integral result using the Kohl-Hopf-Grassberger transformation. Just see whether you get the same thing or whether there are some differences along the way. All right, now to the next step along the way. We now look at interacting particles. And what I mean by interacting is not chemical reactions. Those are also interactions between the particles. I mean physical interactions based on some pairwise interaction, so on some pairwise interaction potential based on pairwise interactions. So remember the way I discussed this last time. If you want something that is characterizing the interactions, you have to modify the hopping rates, because the hopping rates that you have are depending on the potential landscape. And these hopping rates then need to be constructed in a way that you respect detailed balance. And one of those constructions, which is not the only one, but one of them, is that you have, say, this interaction potential, ui, uj, and you choose as a hopping matrix something based on what's called the heat bath rule. Okay, I'm missing a factor of 2 here. It's 2d divided by that. And the interaction, that's what I said here by pairwise interactions. We have locally a value of the potential at some time t. And the reason that there is a local potential is because there's other particles that interact with the particle at side Ri through a pairwise potential. Right? So here's this pairwise potential V between Ri and Rj. I sum over all j, and those j's may be, all the particles in the system, depending on really what the range of the interaction is. That's why I'm not constraining it to nearest neighbors. And then I have to account for the fact that this interaction is, of course, only there if I actually do have some particles at that side j, and it will scale accordingly. The more particles I have, if this is a pairwise interaction, the larger the amplitude of the interaction will be. Okay? So now that you have this, the important feature of such an interaction is that our dij's, they now depend on the actual distribution of the particle numbers throughout the lattice. Okay? So they are functions of nj. And then you really break the symmetry between being allowed to choose between coherent states and the Kramers-Moyal type of description, because in the coherent state formalism, you don't have the ni's as variables. We choose to sacrifice those variables for a field, which is the mean that comes up in the marginalization. So there's no obvious way of how to actually implement such a configuration-dependent diffusion coefficient in the coherent state path integral. But there is one clearly here when you look into the Kramers-Moyal path integral description, because that's formulated in terms of these particle numbers. So again, what we would like to have is a continuum limit in the sense I've been talking about. You coarse grain over a certain length scale, at least the scale of nearest neighbors. And then you write out the various terms. The first thing we want is we want an expansion of this term that appears in the hopping. So in a discrete version, this was Ni and J, the corresponding tilde fields, right? And from that we constructed yesterday just these diffusion terms. So those two terms were what we got out from the analysis, where we didn't account for any kind of potential. Now we have a potential, so there will be more terms. Not here, but later on. So when you have that here, you get I nj minus ni, just a simple Taylor expansion, 1/2 complex unit nj minus ni, and then we have a square plus higher order terms, order nj minus ni to the third. And the hopping rates, that's now, which is different. So before this was a constant. Now I have dij. So remember, this is our expression. I have dij given in terms of such a heat bath rule. And now I'm doing the same thing. I'm trying to expand to leading order. So this will then be also just a 1. That turns into a d. And then minus 1/2 times d over kBt times uj minus ui plus, again, higher order terms that you might get. So now that I have these individual terms expanded out, I can look at the full term, which says I have to sum over all neighbors of I. And there I have this expression dji, ni e to the I, and those two terms I just wrote down. This one is the nj tilde minus ni tilde minus 1. Okay. And now just have to use what I wrote in the above two lines, insert it here, and multiply everything out. So what you get is a sum over all neighbors of I, ni, and then in the brackets, d complex I nj minus ni tilde plus 1/2. These terms are not new for you. They are just the same terms as I got them previously. Okay, right, this is what you get if there is no potential at all. And they give rise to the terms which are just underneath on the second blackboard. The real new term is this one. It's minus 1/2 d over kBt. uj minus ui, and then complex unit nj minus ni tilde fields. Okay, and higher order terms that we do not consider. All right, now we know how to do the continuum limit. This is from before. That here turns into a lattice, or that is a lattice Laplacian, so it turns into a Laplacian. And this is the gradient of n tilde squared. The only thing that we're missing to look at is the third term. And for that third term, we have 1/2 times d over kBt a squared. I'm just putting here the proper terms with the lattice constants, so a squared, and then summing over all neighbors, minus ui over a, then I nj minus ni tilde also over a, right? So you see what I did? I put the a squared in front and divided by a at each of those terms. I'm doing that because this expression and that expression then they are difference quotients, so they turn into nabla operators. So we have nabla u times nabla n tilde. That means, and the a squared I combine, so in the limit of a going to 0, this will turn into a to the d over kbt. So that's what I'm doing here. This is now my new d. Let's call this d tilde. That's my macroscopic or mesoscopic diffusion coefficient. And this a to the d I need for the rewriting of my density as my particle number as a density. And then I do have the gradient of the potential scalar product with the gradient of complex unit times the response field n twiddle. Good, we're almost there. Now take everything together and write it all in the action as a function of now these continuous fields n and n tilde. It's an integral over space and time. And I do have all the terms that we had before. Okay, so let me write them out anyway. This is I n tilde dtn minus the nabla squared n, so the diffusion equation part. Then the noise term, we had all this already, dn nabla I n twiddle squared. And now the new term that we have is minus d over kbt times I tilde n nabla dotted into n times nabla u. Okay. And I could add, but I don't, I could add also here any kind of chemical reactions along the way. This is just now focusing on the Brownian motion of the particles, so the hopping, and the hopping modified by the fact that you have an interaction potential between the particles. Good. Now, we're not finished yet. Here on this right-hand side, we have an additional term that comes from the interaction potential, u, but we still need to insert what this u actually is. It is the interaction that we have in the system, so it's the sum over the pairwise interaction. So what you then get is the new term from the interactions. It looks like minus I response field RT, and then you get the gradient d over kbt integral over r prime n of r and t gradient of v of r minus r prime n of r prime and t. So you see, right, because you know, if you want to know the term that is in the equation of motion, It's just that one, right? This is what you then include in the equation of motion. And now you have to think a little back when we talked about interacting Brownian particles. That's exactly the term coming from the interaction between Brownian particles via forces that are driven by the pairwise interaction potential. So you have the gradient of the pairwise potential, and you multiply the density at position r with the position at r prime. And that coefficient here in front is d over kt. Now you have to remember the Stokes-Einstein relation. This is the mobility coefficient. Okay? So you do indeed have a term which says dTn is diffusion and pairwise interaction. The pairwise interaction is via forces that are acting on the particle through a friction or mobility term. So that means we have derived the Langevin equation for our field theory N of R and T. Okay, caveat along the way. This is all a coarse graining procedure, and we have done expansions along the way which are not rigorous, but only rigorous if we can coarse grain and take the continuum limit. Else you might want to question what you get. But if those things are valid, these limits, then this is a proper field theory that you can derive.